Hey guys, welcome to question MM413 of the Maths Methods Fortify study guide. So, Jai the beekeeper has multiple beehives in his backyard. The weight of the honeycomb contained in any given hive, X kilograms, is a continuous random variable given by the probability density function shown below. So this one here. Part A is a 2-mark question, firstly. Part A says, show that B equals 4. Awesome. So that's this B here. Now, first things first is to recognize that in a probability density function like this, the total area under a probability density function is equal to 1, okay? So our total area is equal to 1, right? And our area is found by doing the integral of 2 to b, or 2 to like our lower to our upper, of the function. So 3 root x over 16 take 4 root 2 dx. Awesome. So now, this might seem a little tricky, but what we can actually do is we can separate the root x and the 3 on 16 take 4 root 2. Because essentially what we're doing here is saying 3 on 16 take 4 root 2 times root x dx, right? Because this root x was just on the top. And the reason that we're doing this is because now we can actually take out this bit here as a constant at the front. And say 3 on 16 take 4 root 2 times from 2 to b of root x, which is the same as x to the power of 1/2 dx. Awesome. Now what we have is still 3 on 16 take 4 root 2 times the integral, which is 2x to the power of 3 on 2 over 3 from 2 to b. Awesome. Now, dividing both sides by 3 on 16 take 4 root 2, we get 1 divided by that, which means that we have 16 take 4 root 2 over 3 equals the integral of this. Okay, so we sub in our b, so we get 2b to the power of 3 on 2 over 3 minus 2 times 2 to the power of 3 on 2 over 3. Awesome. Now, we can simply just keep evaluating this. What we get is 16 take 4 root 2 over 3 equals 2b to the 3 on 2 over 3, and then 2 to the power of 3 on 2 is 2 root 2, so we get minus 4 root 2 over 3. Multiplying both sides by 3, we get 16 take 4 root 2 equals 2b 3 on 2 take 4 root 2. Now these 4 root 2's can cancel, so we get 16 equals 2b to the 3 on 2. Dividing both sides by 2, we get 8 equals b to the 3 on 2. And then we can do both sides to the power of 2 on 3. And the reason that we do that is to cancel out our to the power of 3 on 2 on that b. Because if we do 3 on 2 to the power of 2 on 3, we get b to the power of 6 on 6, which is b to the power of 1. So just normal b. Now 8 to the power of 2 on 3 is equal to 4. So therefore b equals 4. Now our first mark comes when we sub in our integration. So basically like the step that we had down here. And then our second mark comes when we find that b is 4. Guys, that's it. We've shown that b equals 4. So let's move on to part B. Now part B is a 2-mark question again. And B, it tells us to find correct to 3 decimal places the value of mu, where mu is the average weight of honeycomb contained in a beehive. Awesome. So, as we know, our average, or our expected value of a probability density function is equal to the lower bound to the upper bound from 2 to b, and we know that b is 4 because we found that in the previous question, of x times f of x, right? I should just say a and b here. So these are our lower upper x times f of x dx, and in this case, of course, our lower and upper are 2 and 4, and then we do x times our, in this case, h of x, so we have 3 root x over 16 take 4 root 2 dx. Awesome, and again we can take 3 on 16 take 4 root 2 out as a common factor, or I should say a constant rather. 3 over 16 take 4 root 2 outside of 2 to 4 of x times root x, which is x to the power of 3 on 2. Awesome. And then we get, just keep that 3 on 16 4 root 2. Multiplied by our integral of x to the 3 on 2, which is 2x to the 5 on 2 over 5 from 2 to 4. Awesome. Now we have, again, just the 3, 16 take 4 root 2, multiplied by, now we can sub in our values, and that's actually our first mark just here. So 2 outside of 4, 5 on 2 on 5, minus 2, 2, 5 on 2 over 5. So it's just our normal integration here. Cool. And then we can keep going from there and say that we have 3 on 16 take 4 root 2 multiplied by 64 on 5 take 8 root 2 on 5. What this gives us is 3.056 kilograms. That's our second mark. So we need to make sure that we do this to 3 decimal places, because that's exactly what the question asks for. And that's it. So guys, let's move on to, that was actually part BI. Let's move on to part BII. Part BII is a 1 mark question, so we're going to be able to do this all in our CAS. And it says, find the value of M, and we're still doing this correct to 3 decimal places, where M is the median weight of honeycomb contained in a beehive. Awesome. So what we've got is, whenever we talk about medians, we talk about the fact that on either side of the median, we have 1/2 of the data, okay? So if we had a probability density function that did something like this, that means that 0.5 of the data lies here and 0.5 of the data lies here if this is our median value, okay? So that's exactly what we're looking for. So we're looking for our area, which is 0.5, from our lower bound 2 to a value of M, okay? So from 2 to our median is 0.5 of the data, okay? Of our function, which is 3 root x on 16 take 4 root 2 dx. Because this is a 1 mark question, we can simply solve this in our CAS. And what we get is M equals 3.083 kilograms. Don't forget your kilograms, because that's important. They're the units. Don't want to miss out on those. Guys, that's our first and only mark for part BII. Let's move on to part BIII. Part BIII is a 2 mark question. And it asks us to find, I'm actually going to just change this. Asks us to find the probability that x is greater than 6 mu over 5, given that x is greater than m. Awesome. So first things first is to figure out what 6 mu on 5 is, okay? Because we're not going to be able to figure anything else out unless we do that. So mu we found was 3.056, which means that 6 mu on 5 is equal to 3.668. Now, what we're looking for here is actually, we know that the probability that x is greater than 6 mu on 5, given that x is greater than m, equals to the probability, this is our conditional probability rule, 6 mu on 5 intersect x is greater than m over probability that x is greater than m. Awesome. So we also know that our median, m, is 3.083, which means that because 6 mu on 5 is greater than our m, the intersect between them is actually just x is greater than 6 mu on 5. Okay? If you think about this like on a number line, if we had our 6 mu on 5 here, oh sorry, no, let's call it our m here, and our 6 mu on 5, which is our 3.668, this is our 3.083. Greater than m is all of this, greater than 6 mu on 5 is all of this, so the intersect between these two is everything from this point forward, which is everything after 6 mu on 5. Awesome. And then what we're looking for is that probability that x is greater than m as well. Awesome. So we know that the probability that x is greater than m is going to be 0.5, right? Because half the data lies above the m value. But we don't know what this probability here is, so we need to figure that out. So the probability that x is greater than 6 mu on 5 is equal to our area from 6 mu on 5 or 3.668 as we found up here, up to 4, right? Of 3 root x on 16 take 4 root 2 dx. Awesome. And this is equal to 0.1888. And this is our first mark here. Now that we've got that, we can work out the rest of it. So again, we know that probability that x is greater than 6 mu on 5 intersect x is greater than m equals probability that x is greater than 6 mu on 5 over the probability that x is greater than m. Now we've just found that the probability that x is greater than 6 mu on 5 is 0.1888. 0.1888 over the probability that x is greater than m. So the probability that it's greater than the median is 0.5 because that's the nature of the median. It has 0.5 above, 0.5 below. What that gives us is 0.3776. And that is our second and final mark for part B, I. And that's it. So guys, let's move on to part C. Part C is a 1-mark question, which means that we can do it all in our CAS without showing any working, if we don't want to. 1 mark. And it says, find the probability that a randomly chosen beehive contains more than 2.5 kilograms of honeycomb. Awesome. So all we're looking for is the probability that x is greater than 2.5, which means that we're looking for the area from 2.5 to 4 of 3 root x over 16 minus 4 root 2 dx. Okay? Because if it has more than 2.5, that means it has more than 2.5, but less than 4, because 4 is our upper limit there. And that means putting that into our CAS, we get 0.7826. That's our first and final mark. Let's move on to part D. Part D is, again, a 1-mark question, and you can actually do this on your calculator. And if you're not too sure how, I'll show you right now. So D, 1 mark. Now, we're dealing with a confidence interval here, okay? So Jai wishes to estimate the proportion of his hives which contain more than 2.5 kilograms of honeycomb. A sample of 30 hives is inspected, and it's found that 20 of them contain more than 2.5 kilograms of honeycomb. Determine the 95% confidence interval for Jai's estimate of the proportion of interest. Give your answer correct to 3 decimal places. Awesome. So the way to do this on your calculator, we're firstly, we're looking for a confidence interval, right? And I'll just rewrite this so that you can see it. And normally we would say that this is our confidence interval. And you can do this, and you can plug in all your values and everything, and you'll get the right answer. But you can do this quicker because it's a 1-mark question. And you can do this all on your CAS. So what you're going to do is grab your CAS, and you're actually going to go to menu 6, so statistics, confidence intervals, and then 1 prop Z interval, okay? And then we know that there's, he's told us that there's 20 that contain more than 2.5 kilograms of honeycomb out of the 30, okay? So we've got 20 successes, 30 total hives, and our confidence level is 95%, so we can leave that as 0.95. Then we can just click enter, and what we get is a lower of 0.498 and a C upper of 0.835. And that is our confidence interval. So guys, that's it. Check that out there. It's really, really useful, especially if you've got a 1-mark question like this. So it's menu, for me, it's menu 665. So it's just the 1 prop Z interval that you're looking for. And that's it. So that is our confidence interval. So we can actually just write that straight out because it's a 1-mark question. Don't need to show any working. So that's our first and only mark for that question. Let's move on to part E. Part E is a 2-mark question. It says if 40 hives are chosen at random, what is the probability that at most 31 of them contain more than 2.5 kilograms of honeycomb? Awesome. So when it says at most, that means everything that it includes and less than that, right? So at most 31 means 31 or less, right? So x is less than or equal to 31. That's what we're really looking for. So what we can say is that because we're choosing 40 hives, each one of them has the same probability to be more than 2.5 kilograms. Each one doesn't affect any of the others. That means that we're going to be dealing with binomial distribution. If you don't understand how I'm coming to any of these conclusions, just hit me up in the comments below and ask any questions that you've got, as always. So, we know that we're going to pull up our binomial CDF, and what we're going to get asked is for four things: lower, upper, N and P. Our lower is going to be 0, right? Because we can have everything less than 31. Our upper is going to be 31. N is going to be 40, because we have 40 chosen. And P is going to be our chance that any given hive is more than 2.5 kilograms. And in part C, we found that to be 0.7826. Okay, so this is where this question is tricky, because you have to link it back to part C. This is our first mark, identifying that. Then our second mark comes from actually writing the answer. So therefore, probability that x is less than or equal to 31 equals 0.514. That's our second mark. So guys, that's our final answer for part E. Let me know if you have any questions about it, but for now, let's move on to part F. Now, part F is completely changing pace and says, Jai likes to extract liquid honey from his hives every Monday, but sometimes the bees have not produced enough for extraction by the next week. If he extracts honey from a hive 1 week, the probability that there will be enough for extraction the following week is 1/3. If he doesn't extract honey from a hive 1 week, the probability that there will be enough for extraction the following week is 9 in 10. On a particular Monday in week 1 of June, he extracted honey from one of his hives. What is the probability that he extracted honey from his hive in exactly one of the following 3 weeks? All right, awesome. So what we're really looking for is a tree diagram, okay? Because we're dealing with conditional probability here. So if he extracts it, this happens. If he doesn't extract it, this happens. So because of that conditional nature and that dependency on a certain event happening, we have to use a tree diagram to kind of visualize this. So what we're going to do is we know that in week 1 of June, he does extract it, okay? So he does extract. Which means that in the first week, he extracts it. So I'm just going to use H because of honey. So he extracts the honey. The next week, he can either extract it or not extract it. So that's week 1. This is week 2. And we're looking for the probability that he extracted honey in exactly one of the following 3 weeks. So we actually need to do 4 weeks worth. So we've got our extracts or not extracts. That's actually not extract. And we've got extracts here and not extracts. And then in week 4, he also can extract or not extract, extract, not extract, extract, not extract, extract, not extract. Extract is a really weird word. So we've got, that's dash there. Now, the first week he extracts it. So if he does, the chance that he can extract the next week is 1/3. So this is 1/3. Because that's 1/3, this is 2/3, because both of these each of these branches have to equal to 1, the pairs of branches. Now, because he's extracted it here, again, he's got a 1/3 chance to extract it, and therefore a 2/3 chance to not. And again up here, 1/3 and 2/3. Now here, he hasn't extracted it, which means that there's a 9 in 10 chance that he will be able to extract it. So 9 in 10, and therefore this is a 1 in 10 to add to 1. Now here, he hasn't extracted it, so the probability that he will extract it the next one is 9 in 10. And again, this is a 1 in 10. Again, here, he hasn't extracted it, so the chance that he does is 9 in 10. This is 1 in 10. Here, he has extracted it, so the probability that he extracts it is 1 in 3, and the probability that he doesn't is 2 in 3. Awesome. So what we're actually looking for is the probability that he extracted it exactly one of the following 3 weeks, okay? So we're looking for paths that only have 1 extraction in them, okay? So we can go 1 extraction here, not, so we want this path, because we've got only one extraction in that path, and we're not including this as part of the following 3 weeks, because we've dealt with this first week, and then we're dealing with the following 3 weeks, okay? So we've got that one, which is only in 1 week. Then we can go not extract, extract, not extract. So we want this path as well because we've only got one extraction there. And then we can also go not extract, not extract, extract. Okay, so we can go for this one as well. So each of these 3 paths only has one extraction exactly one extraction in the following 3 weeks. Okay, so how do we figure out the total probability of these? Well, we add all these together for each one, and then we add all of those together. So what we get is the probability equals this branch, so 1 in 3 times 2 in 3 times 1 in 10. So that's this bit here, that's this bit, plus this branch here, which is all of this. So 2 in 3 times 9 in 10 times 2 in 3, which is that one there, and then plus 2 in 3 times 1 in 10 times 9 in 10. This is our first mark as well. Just drawing all this gets our first mark. Awesome. And then from there we can say that this is equal to 2 on 90 plus 36 on 90 plus 18 on 90, which gives us 28 on 45. And this is our final answer, our second mark. So guys, 28 on 45 is our final answer for FI. Let's move on to FII. Part FII is also a 2-mark question. We're actually going to use this tree diagram again, so I'm not going to rub it out, but I haven't given myself much room here. I'm actually going to rub out this bit here. So if you need that, just write it down. Okay. Alrighty. So we've got this tree diagram still. And part FII says that he extracted honey from his hive in week 2 of June, given that he extracted honey from the hive in week 3 of June. Alright, so what we're saying is, he's extracted it in week 2, given that he extracted it in week 3. Okay, so we're talking about him extracting it in week 2 intersect week 3 over the probability that he extracted it in week 3. Awesome. So the intersect between him extracting it in week 2 and him extracting it in week 3 is that branch, right? So he's extracted it in week 2, and here he's extracted it in week 3, which means that the intersect between those two is these probabilities multiplied together. So we get 1 on 3 times 1 on 3. That's our intersect, that's this top part, over the probability that he extracts it in week 3. Okay, so him extracting in week 3 is this and this. So what we have to do is get the total probability of him getting to this point, which is 1 on 3 times 1 in 3, so this branch to here, and then 2 in 3 times 9 in 10 here. Okay, so what we get is 1 in 3 times 1 in 3, which is this branch here, and then to get to this branch we add 2 in 3 times 9 in 10. This is our first mark. Now our second mark comes from our final answer, but working on the way, 1 on 3 times 1 on 3 is 1 in 9, and then we get 1 in 9 plus 18 on 30, which gives us eventually 5 over 32. And 5 over 32 is our second and final mark for part FII. And guys, that actually wraps up MM413. If you have any questions about any of this, please let me know in the comments below. But otherwise, thank you for watching, and I'll see you in the next video.